Matthews Gatos here. In this video, we will look at the second derivative test, section 5.4. You'll remember the second derivative that we did in the last lesson was used to find intervals of concavity. So in this one here, we're not going to use the intervals of concavity. We're going to find the first derivative and the critical values that make the first derivative equal to 0, and then substitute them into the second derivative just to see if they're positive or negative. So 3 different things can happen. Firstly, the first derivative can be 0 and the second derivative can be positive, which means that it would be concave up, smile, which means it has a minimum. The second thing that can happen is the first derivative is 0, the second derivative is negative, and then I would have a concave down, a frown, which means I have a maximum. And then the last thing that can happen is that the first derivative and the second derivative are both equal to 0. In that case, the second derivative fails. So we can't use the second derivative test to figure out if I have a max or a min. I need to go back to the first derivative and look at intervals of increase and decrease. So what I'm looking at is values that get really close to that critical value. So couple things can happen. First thing is the first derivative can change sign. So let's say if it was increasing on the left and decreasing on the right, in that case I would have a maximum. Or I could be decreasing on the left, increasing on the right, and in that case I would have a minimum. The third thing that could happen is I don't have a sign change, and in that case I am going to have a point of inflection. So you can see here, these are both points of inflection because the concavity changes, but in the first case, I'm always increasing. The function is increasing. Or here, I'm always decreasing. So no sign change indicates a point of inflection. Now, it's important to note that the second derivative only applies when the first derivative is equal to 0. If the first derivative is undefined, the second derivative will also be undefined. So let's summarize that here. So we have a couple, we're putting everything together, first derivative and second derivative. So if the first derivative is greater than 0, that means that my function is increasing. If my first derivative is negative, that means I am decreasing. And if my first derivative is equal to 0, that means I have a local max or min. I can have a local max or min. Now let's pair that with the second derivative. So looking at the second derivative, if it is greater than 0, I'm concave up. So in this last one, I had a local max or min. If I'm concave up, I therefore have a min. If my second derivative is less than 0, that means I'm concave down. So in this one here, I had a max or min. Because I'm concave down, I actually have a max. If the second derivative is equal to 0, so increasing function, second derivative equal to 0, possible inflection point. If the first derivative is less than 0 and the second derivative is equal to 0, again, a possible inflection point. And then if I have that special case where the first and the second derivative are both equal to 0, the second derivative test fails. And remember, one of 3 things can happen. You can have a max, a min, or a point of inflection. So let's look at all of this graphically. Okay, so here you can see I have a function, and I'm going to be looking at different points on that function and what those points mean for the function itself, for the first derivative, and again for the second derivative. So for the function itself, I'm going to look at y values that are above the x-axis, and in that case, it means they are positive. So look at these points here where it is above the x-axis. So for those points there, the function is positive. Then I'm going to look at points where it is below the x-axis, like here, here, and those points there, it would be negative. So at A and D, it's negative. Okay, same graph, let's look at first derivative. So first derivative, again, is the slope of your tangent lines. So let's look at any point where it is positive. So I see one point here, the slope is positive. Okay, let's look at another point here, right here, also positive. I think that's it for the positives. Let's look at negative. So negative is where the slope of the tangent line is negative, so that would occur right there. Okay, and then when the first derivative is equal to 0, that occurs when I have a horizontal line. That's when the slope is 0. So if I have a horizontal line, the slope is 0. And that's going to occur anytime I have a max or a min. So you can see here, 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 and here. So those all have a slope of 0. So at A it's 0, at D it's 0, at F it's 0, and at G it's 0. So the only thing I have left to consider is what's happening at C. And you can see here I have concave up meets concave up. Right there is a cusp. And we know that at a cusp it is not differentiable. So this point here, the first derivative, does not exist. So I need to remember at for the first derivative at x equal to c, it does not exist, because when I look at second derivative, I also know it doesn't exist. So if the first derivative doesn't exist, then the second derivative automatically does not exist. So for the second derivative, I'm going to look at intervals of concavity. So I'm going to mark where it is concave up. I'm also going to mark where it's concave down. So any point where it is concave up, any point that lies on where it's concave up, the curve is going to be above the tangent lines, so it will be positive. So that means that A is positive, B is positive, C does not exist, D is positive. And then I look at where they are concave down. So any point on concave down, E, F, G, and H. Okay, and you'll notice the inflection point right here where it changes from concave up to concave down. Okay, so now let's look at these algebraically. So algebraically, what I want to do is I want to find the first and the second derivative. I'll start there. So first derivative, 3x squared minus 12. Second derivative, 6x. Okay, I want to find the critical values, which are the values that make the first derivative equal to 0. So factoring out the 3, I end up with a difference of squares. So my critical values are at positive and negative 2. I'm going to use those in the second derivative just to see, is it positive or negative? So the second derivative at 2, I'm going to have 6 times 2, which is 12, and that is positive. Second derivative at negative 2. I'm going to have 6 times negative 2 is negative 12, so that is negative. So since it's positive, that means it's going to be concave up, which means it has a minimum. So a minimum at x equal to 2. Put in 2 for the original function to figure out what the y value is. So 2 cubed minus 12 times 2 plus 5. So the y value that goes with that, negative 11. So I have a minimum point at 2 and negative 11. Okay, for the second derivative at negative 2, that's concave down because it's negative. So that means I'll have a maximum at x equal to negative 2. So y equals negative 2 cubed minus 12 times negative 2 plus 5. So that y value is 21. So I will have a maximum point at negative 2 and 21. So I always like to put those into my calculator just to check to see if I've done it right. And you can see on my calculator I have a max at negative 2 and 21 and a min at 2 and negative 11. So I know I did that correctly. Okay, let's look at another one here. So at this one here, I'm going to again find the first and the second derivative. So first derivative, 4x cubed minus 24x squared. Second derivative, 12x squared minus 48x. Okay, so let's find the critical values, which are the values that make the first derivative equal to 0. So factoring out 4x squared, the GCF, I'm left with x minus 6. So my critical values will be at 0 and positive 6. And I'll put those into my second derivative. So my second derivative at 0 is 12 times 0 squared minus 48 times 0, which is 0. My second derivative at 6 is 12 times 6 squared minus 48 times 6, which is 144. Okay, so my first derivative is 0 and my second derivative is also 0, which means that the second derivative test fails for x equal to 0. So I need to go back to the first derivative and figure out what's happening at 0. So remember, 3 things can happen. I could have a max, I could have a min, or I could have a point of inflection. So back to my first derivative. I've got 4x squared, which is 0 here. But to the left and the right, it's always going to be positive since I'm squaring. Okay, x minus 6 is 0 right here. So to the left, it's negative. To the right, it's positive. So I'm really interested what's happening on either side of 0. So I have a negative, which makes that decreasing. And I have another negative on this side, which makes that decreasing. And well, let's just look at this too. That's increasing. So I can see what I'm really interested in here is what's happening at x equal to 0. So since it's decreasing on both sides, that tells me I have an inflection point at 0. So it's going to be kind of like that because it's decreasing. If I put in x equal to 0 into the original equation, I'm going to have y equals to 0 to the 4 minus 8 times 0 cubed. So that's a value of 0. So I know I have an inflection point at 0, 0. Now, in the first derivative, I can clearly see for x equal to 6, if I'm decreasing on the left, increasing on the right, I do have a minimum value. But I can also see that here as well because it's positive in the second derivative, which means it opens up and has a minimum. So both of them kind of tell me that I have a minimum. So when x is equal to 6, y is equal to 4 times 6 cubed minus 24 times 6 squared. The y value there is negative 432. So I know at 6 and negative 432, I have a minimum value. And I always like to check those graphically just to make sure that I am correct. So let's see if I do have an inflection point at 0, 0 and a minimum at 6 and negative 432. So putting that in my calculator, I can see that yes, I am right. Okay, so last example here, we have quotient. Okay, so because we have a quotient, the second derivative will be a little bit more challenging to figure out. So in this case here, I'm okay with us just using the first derivative to help us find intervals of increase and decrease, thereby finding maxes and mins. So remember, for quotient law, I have low d high minus high d low, draw a line and square below. So my first derivative is low, d high means derivative of the high, which is 1, minus high, and then d low, derivative of the low, is 2x, all over the low squared. Okay, so tidying this up, I'm going to have negative x squared plus 1, because here I have negative 2x squared plus the x squared is negative x squared, all over x squared plus 1. And I always want my leading coefficient to be positive, so taking out the negative, I would create a difference of squares. Okay, so my critical values only in the numerator would be 0 and negative 1. The denominator is defined for all real numbers, so positive and negative 1 are all I need to use. Okay, so first thing I'm going to do, since this is a negative, I'm going to put a negative in all my categories. X plus 1 is 0 here, so to the left it's negative, to the right it's positive. X plus 1 is 0 here, so to the left it's negative, and to the right it's positive. And then this, because it's squared, added 1, and then squared again, will always be positive. So in this interval I have 3 negatives, which means it's decreasing. 2 negatives mean it's increasing. 1 negative means it's decreasing. So if I'm decreasing on the left, increasing on the right, that means this must be a minimum. If I'm increasing on the left, decreasing on the right, this must be a maximum. So let's put those into the original equation to figure out the y value that goes with them. So when x is -1, I have -1 over -1 squared plus 1, which is just equal to -1/2. When f is at 1, it's going to be 1 over 1 squared plus 1, which is just +1/2. So what that means is that I have a minimum at -1 and -1/2, and I have a max at 1 and +1/2. Again, I always like to put those into the calculator just to check to see if I've done it correctly. And you can see I do in fact have a max at -1 and -1/2 and a min at 1 1/2. Okay, so that's it for the second derivative test, section 5.4. Before I bring on your homework, I want to bring you back to 1978, where this gem of a song was released. Gloria Gaynor. Great song, back from 1978, still a classic today in my opinion. I thought we could just change this into a calculus song since we're doing the second derivative test. Call it I Will Derive. I Will Derive. Maybe it'll catch on. Textbook questions, page 232. Hope this video helped, and I'll see you for the next one.